as always. All right, well, let's get started. And this is just some review for chapter 14, or review, or practice, whatever you want to call it. Let's start with, and this is again chapter 14, carboxylic acids and their derivatives. I want to start by looking at question 14.13. So this is question 14.13. And I'll just read it. It says, which member of the following pairs has a higher boiling point? So we'll just write it like this. Which has higher boiling point? Okay. And in A, it says pentanoic acid or pentanal. So we're comparing pentanoic acid and pentanal. So what we'll do is we'll draw the bond line structures of both of these, and then we'll compare them. And I'm sure that some of you, it's very quick to answer if you probably know it already. But let's just take a look at the two compounds. If we look at pentanoic acid, it's a carboxylic acid, and it's got 5 carbons in it, right? Pentanoic acid. So we'll start by drawing our carboxyl group. We have 1, 2, 3, 4, 5 carbons, so that's pentanoic acid. And pentanal, since we have the suffix al, we know that this is an aldehyde, right? So this is an aldehyde. And so to draw pentanal, we'll put our carbonyl with a hydrogen attached to it. And then we're going to have 5 carbons as well. So we have 1, 2, 3, 4, 5, like that. Does anybody have an idea which one of these would have a higher boiling point? You can unmute your mic or type it in the chat. If I look at the type of intermolecular forces that each of these molecules possess, okay, and I look at the strongest intermolecular forces, you should know that intermolecular forces, IMFs, start with the weakest, which are London forces. So all molecules possess London forces. Then we go from there, and we can have dipole forces, and that's for molecules that have permanent dipoles. And then we go to hydrogen bonding. Well, if you look at the structures of these, you can see that pentanoic acid has an oxygen-hydrogen bond, and that is one of the requirements for hydrogen bonding. And so pentanoic acid can participate in hydrogen bonding, whereas in pentanal, there is no oxygen-hydrogen bond, and there certainly isn't a nitrogen-hydrogen or a hydrogen-fluorine bond. And so the strongest intermolecular force in pentanal will be a result of the permanent dipole, right? You should know that a carbonyl has a dipole moment going this way. And so the strongest intermolecular force here will be the dipole force. And so the one with the higher boiling point is going to be the pentanoic acid. Yes, the pentanoic acid also possesses a dipole here and a dipole here, and those are great, but those forces are not as strong as hydrogen bonding. Let's take a look at the next one. Again, same question. Which one of these has a higher boiling point? Now we're looking at 3-pentanone or 2-pentanol. So if I have 3-pentanone versus, what was it again? 2-pentanol. So if I have 2-pentanol. Well, if I look at 3-pentanone, it is a ketone because it ends in the suffix -one. We know that it has 5 carbons because it has pent, which means 5 carbons. And we know that the carbonyl for the ketone is going to be at carbon number 3. So if I write it out like this, if I have 1, so if I put my ketone here, if I have 1, 2, 3, 1, 2, 3, 4, 5, like that. So that would be 3-pentanone. And if I draw 2-pentanol, I have to have 5 carbons, 1, 2, 3, 4, 5. But pentanol, when I have the suffix -ol, that means that this is an alcohol. So on the second carbon, I'm going to put a hydroxyl here. Now again, if I look at these two compounds and I compare the types of intermolecular forces that each one possesses, could anybody tell me, based off of this summary that we looked at a couple minutes ago, which one of these would have the higher boiling point? Would it be 3-pentanone or 2-pentanol? Absolutely. Thanks, Sadie. You're all correct, right? It's 2-pentanol. Why? Because pentanol has an oxygen-hydrogen bond, and so it has the capability of doing hydrogen bonding. Okay. If you look at 3-pentanone, yes, there's a permanent dipole because there's a big enough difference in electronegativity between carbon and oxygen, but a dipole-dipole force just isn't as strong as hydrogen bonding, dipole. And so therefore, the one with the higher boiling point is going to be the alcohol, 2-pentanol. All right. Next, if we look at C, okay, if we look at C, we'll try one more. It says 2-pentanol versus pentane. So hopefully this one will be pretty quick. 2-pentanol, which we just drew, versus pentane. Well, pentane is an alkane, right? It's a 5-carbon alkane. So 1, 2, 3, 4, 5. And if we redraw 2-pentanol, 1, 2, 3, 4, 5, and we put our hydroxyl here, hopefully you can see pretty quickly that 2-pentanol is going to have a much higher boiling point because it possesses hydrogen bonding. So the forces that hold molecules of 2-pentanol together are going to be much stronger than the forces that hold an alkane together. Who could tell me what are the types of intermolecular forces that are experienced between molecules of pentane? This goes back to the alkanes chapter. Could anybody tell me which intermolecular forces pentane experiences in a sample? If I have Avogadro's number of pentane molecules, what intermolecular forces hold those together? Well, there's no dipole in pentane, and there's no hydrogen bond in pentane. Therefore, the only intermolecular forces in pentane are London forces. Okay, we've gone over this a few times, but in an alkane, the only types of bonds are carbon-carbon bonds and carbon-hydrogen bonds, both of which are nonpolar. Right? So if there's no polar bonds in the molecule, the only possible intermolecular forces that can be experienced are London forces, and therefore the 2-pentanol is going to have a higher boiling point. If we summarize everything that we learned in this question so far, we see that an alkane has the lowest boiling point. Okay, so out of all the things that we looked at here, lowest boiling point. Then after an alkane, we had an aldehyde and a ketone. So aldehyde, and a ketone. And an aldehyde and a ketone, they usually have boiling points that are very similar. So I wouldn't ask you to differentiate between the boiling point of an aldehyde or a ketone. Then after that, we had an alcohol, which has a higher boiling point. And then if we compare an alcohol and a carboxylic acid, I'll help you out with this. Generally speaking, a carboxylic acid will have a higher boiling point than an alcohol, okay? So it's important that you're able to rank compounds with different functional groups in terms of their relative boiling points. All right, well, let's move on from there. And I want to take a look at question 14.29. So it says here, it's just a nomenclature problem, 14.29. Hopefully you watched the videos and have been practicing your nomenclature. So question 14.29, all it asks us to do, it says write a condensed formula and a line formula for each of the following carboxylic acids. In the interest of time, I'm just going to make it simple and let's say draw the line or the bond line formula. Okay, nothing else. Let's get some practice in this. So the first one is 3-methylhexanoic acid. So we have 3-methylhexanoic acid. Well, if it ends with oic acid, we know that it's some kind of carboxylic acid. If it's a hexanoic acid, we know it's a carboxylic acid with 6 carbons. We could even start with that. We could say, okay, here's my carboxyl group like this. I have my first carbon right there, so I'm going to go 1, 2, 3, 4, 5, 6. You can number them if that helps. Some students really like to do that. There's nothing wrong with that at all. Sometimes I do it. Okay, and then we have a methyl group on the 3rd carbon. So we look over here. There's the 3rd carbon. Perfect. I'm just going to erase the number 3, and we'll draw in our methyl group like that. And there you go. That's 3-methylhexanoic acid. Nothing wrong with that. Well, let's move it out of the way, and let's try another one. I'm going to write down the next two, and if you hopefully have a pencil handy, I'd like you to give them a try. So the next one is 2-ethyl 2-methyl pentanoic acid. So 2-ethyl 2-methyl pentanoic acid, pentanoic acid. So I'd like you to give that one a try. And C is 3-methyl cyclopentane carboxylic acid. So 3-methyl cyclo. All right, so I'll give you a second to think about both of those. Again, hopefully you have a pencil and a piece of paper handy, or a napkin even, and just scribble down the answer. All right. Well, let's do the first one here, or B, 2-ethyl 2-ethyl pentanoic acid. Let's start by drawing the parent, which is pentanoic acid. It's a carboxylic acid. It's got 5 carbons, so we'll go 1. So this is the first carbon. 1, 2, 3, 4, 5. There we go. We can number the carbons if that helps. We have 1, 2, 3, 4, 5. On the second carbon, we have an ethyl group and we have a methyl group, right? We have 2-ethyl and 2-methyl. So that means that that second carbon is pretty busy. It's going to have an ethyl group. How do we draw an ethyl group? We go CH2, CH3, and it also has a methyl group, CH3, like that. There you go. 2-ethyl 2-methyl pentanoic acid. Give me a thumbs up if you followed me on that one. Hope you did. Or let me know if you have a question about that one. Drawing a carboxylic acid. Okay, great. Thanks, Lisa. Perfect. Well, let's move on. Let's try the next one. So 3-methyl cyclopentane carboxylic acid. When you have a carboxyl group, so a carboxylic acid functional group coming off of a cycloalkane, you name it with the name of the cycloalkane, and then you just follow it up with carboxylic acid. So cyclopentane carboxylic acid is nothing more than this. You draw a cyclopentane, 1, 2, 3, 4, 5 carbons like that. Then you add a carboxylic acid to it. So there's my carboxylic acid. By de facto, the carbon that has the carboxyl group, this is called a carboxyl group. The carbon that has the carboxyl group attached to it, that's going to be carbon number 1. It just takes on the identity of carbon number 1. All right. Well, we've got that. We can number 1, 2, 3. And if you said, Mr. Dion, I wanted to go clockwise, 1, excuse me, 2, 3, you can do it that way. Either way, you're going to get the same answer. So here we're going to put our methyl group. So we'll just draw a line here for CH3 like that. And there you have it. 3-methyl cyclopentane carboxylic acid. All right. Let's move on from there. I wanted to take a look at question 14.31. It just asked us to name some compounds. And what does it say here? It says, name the following carboxylic acid using both common and IUPAC nomenclature systems. Well, let's do some review about the naming of carboxylic acid. So the first, if we look at the first 5 carboxylic acids, okay? We look at number of carbons. So we could have 1, 2, 3, 4, or 5. We can look at the structure. We could draw them all out. And then if we look at the IUPAC name here, and then lastly, we'll look at the common name here. All right. Well, let's see if I can draw a straight line. Straight enough. All right. So if we have 1 carbon, our structure is going to be this. It's just going to be a carboxyl group with 1 carbon. So we're going to have a hydrogen here. The name of that compound, the IUPAC name would be methanoic acid, right? Because it's only got 1 carbon. If you have a 1 carbon alkane, it's methane. So this would be methanoic acid, like that. The common name, however, has to be memorized, and the common name is formic acid. Okay, formic acid. All right, and if you think, well, that's pretty close to formaldehyde, which I learned earlier on. Yeah, it is pretty close to formaldehyde. All right, so if you understood the Latin names or the common names of the aldehydes, then the carboxylic acids aren't much of a stretch. If we go to 2 carbons, then we would have a carboxylic acid that looks like this. The IUPAC name is ethanoic acid, so ethanoic acid. And its common name is acetic acid. It's the acid that's found in vinegar. If we go to 3 carbons, we're going to have a carboxylic acid that looks like this. Here's where the IUPAC and common names kind of get a little bit of a tongue twister here. The IUPAC name is propan, so propanoic acid, right? We take propane, we drop the E, and we end it with oic acid, right? That's how we come up with the IUPAC name. All right, well, we have propanoic acid, and the common name is propionic acid. I know you might find it annoying, but I didn't make up the rules, okay? It's just the way it is, and it's still very commonly used by scientists. So propionic acid. If you have 4 carbons, okay, so if we have 1, 2, 3, 4, we have butanoic acid, so butanoic acid. And the common name is butyric acid. And for the 5th one, and this is as far as you have to go, there are other common names, but you don't have to memorize them in this class. If we have 5 carbons, we have 1, 2, 3, 4, 5. This would be pentanoic acid. We discussed that tonight, pentanoic acid. And the common name would be valeric acid. All right. And again, the common names, we saw all of these prefixes when we looked at the aldehydes. We had formaldehyde, acetaldehyde, propionaldehyde, butyraldehyde, and valeraldehyde. Okay, but you have to be aware of all the IUPAC names and all of the common names for the first 5 carboxylic acids. Okay, something that everybody who takes this class, everybody who's gone before you, and everybody who's going to come after you, you all have to memorize those IUPAC and common names for the first 5 carboxylic acids. Well, with that in mind, let's take a look at that question. So it's 14.31, and I'll try to squeeze it on here if I can. 14.31, and the first one is this. I'll just draw it out the way they have it. Okay, so we'll leave that one there. The next one is, I'll draw the bond line structure of the next one. There we go, and C is this one. All right, I'll give you a second to look at those and see if you can come up with a IUPAC name and a common name for all of you. You can start with the IUPAC, you can start with a common. I'll give you a second. While you're doing that, I'm just going to grab a drink of water. I'm curious as to whether any of my students have a name for the first one. And it's not a trick. There are no trick questions in Chemistry 102. Mr. Dion does not like trick questions. Does anybody have a name for A? Yeah, thanks, Sadie. Absolutely. Absolutely. It's methanoic acid, right? So this is methanoic acid, or we can call it formic acid. Let me use a different color maybe for the common name. So, or formic acid. Formic acid. The next one is not something that's just come straight to the table. In fact, the next two don't come straight to the table, do they? Let's come up with an IUPAC name for this one here. You can see that we have a total of 1, 2, 3, 4. So this must be some kind of butanoic acid. And on the third carbon, we have a methyl group. So this would be 3-methyl butanoic acid. Now remember, when we're coming up with common names, we don't use numbers. We use Greek letters, lowercase Greek letters, and they don't start at the carbon. Oops, I didn't mean to write that. They don't start at the carbonyl carbon. They actually start after this carbon. So we have alpha, beta, and then gamma here. This is some kind of butyric acid, but our methyl group is on the beta carbon. And so this would become beta methyl butyric acid, beta methyl butyric acid. All right, well, the next one, again, I'm not a fan of the trick question, so there's no trick here, but there's something I find a little annoying about this question being in the book. I mean, I'm talking about this one right here, because the book covers the IUPAC nomenclature of this, but it doesn't, I don't think it covers the common nomenclature. I'll show you quickly. I'm not going to ask you about the common nomenclature of a cyclic carboxylic acid or a cyclic compound that's a carboxylic acid, but just to show you, we have a total of 5 carbons, so this is a cyclopentane, and then we have a carboxylic acid, so this becomes, the IUPAC name would be cyclopentane carboxylic acid. Now, if you understand the common names, you'll see where this comes from. But the common name, again, I don't think this is covered in our book, and I've read the book a few times. It's cyclovaleric carboxylic acid. So instead of cyclopentane, you call it cyclovaleric carboxylic acid, okay? Anyhow, it's kind of annoying because I don't like it when things aren't covered in the book, but cyclovaleric carboxylic acid, okay? So read my lips, okay? I am not going to ask you to give this kind of name, okay? A common name for a cyclic carboxylic acid. Not going to happen, okay? But all the other are totally legit, totally fair for this class. All right, let's move on to question number 37. No, let's move on to something that's a reaction. I wanted to move on to something that's a reaction. Let's do question 14.43. This is a good one. Yeah, I like these kind of conceptual questions where I just ask you to explain a concept. So question 14.43, if you look at our book, it says, write the general equation showing the dissociation of a carboxylic acid and water. So dissociation of a carboxylic acid in water. Okay, now to solve this problem or to answer this problem, you're going to have to go back to your general chemistry, right? Your chemistry 101, if you took your introduction to chemistry class at PPCC, which I think a lot of students did. Now, a carboxylic acid is an acid, obviously. That's why the word acid is in the name. But a carboxylic acid is not a strong acid, okay? You can even write that down here if you want. That carboxylic acids are weak. They're weak acids. They are acids, but they're weak acids, okay? Now, how do you denote that something is a weak acid? Let me show you. If we draw a general structure of a carboxylic acid, right? Just draw the functional group. We have R, and there's our carboxyl group. Well, if we put that acid, that carboxylic acid in water, how do we show that it's weak? The way that we show that it's weak is we use reversible reaction arrows like this. That means that the reaction can go forward, but it can also go in reverse. All right? Now, what is an acid? An acid, according to Bronsted-Lowry definition, an acid is a proton H+ donor, and a base is an H+ acceptor. And here, water is going to behave as a base. So a base is a Proton Acceptor. Now, where's the acidic proton? In a carboxylic acid, the acidic proton is that one right there. So the carboxylic acid is going to donate this proton to water. Now, what would that give me? Well, we would end up with our carboxyl without the hydrogen. Now, if this is neutral and it's lost H+, what must be left over? Right? If you start with 0 and you end up with something that is, if you take 0 and you subtract -1 from it, okay, we do it like that. You subtract -1 from 0. What do you get? You get +1. Okay? So that means that when we subtract, sorry, I meant 0 minus 1 because there's a +1 charge, we end up with -1. That's what I meant. So we have a negative charge on our carboxyl, which now becomes what's called a carboxylate, and we end up with H3O, which has a +1 charge. All right, now you need to be aware of what these are called. This is called a carboxylate, right? Think about things in chemistry that have negative charges. Nitrate, sulfate, carbonate, right? Carboxylate, okay, so that denotes a negative charge. And H3O plus is called hydronium. Okay, and that goes way back to your acid-base studies when you took Introduction to Chemistry 1. So a carboxylate and a hydronium. And again, the way that we show that the carboxylic acid is a weak acid are by these reversible arrows here, right? Okay, give me a thumbs up if you follow me on that concept. Even if you're with me part of the way, like Mr. Dion, I might need to think about it. But I get the idea. Is anybody with me on that? Okay, cool. Well, good. I'm happy to see you're getting there. Yeah, it's not an easy subject, right? Now, the question isn't asking this, okay, but something I just want to address with my students who are here. Now, a carboxylic acid, again, is a weak acid. If you go back to your Chemistry 101, okay, you're all enrolled in Chemistry 102, but if you go back to your Chemistry 101 days, you probably spent more time talking about strong acids. Now, let me give you an example of a strong acid. And I know you could all come up with a strong acid like nitric acid or sulfuric acid or hydrochloric acid. Well, hydrochloric acid is a strong acid. And when you put hydrochloric acid in water, it ends up donating a proton to form chloride, which is left over, plus the hydronium. The difference is this. It's the arrow that goes here. When you have a strong acid, the arrow is irreversible. It's in one direction, okay? So that's the difference between a strong acid and a carboxylic acid, which is a weak acid. Okay, so that's the dissociation of a carboxylic acid in water. All right, this is what in question 14.45, that's where I wanted to go next. Question 14.45. There we go. It says, what reaction occurs when a strong base is added to a carboxylic acid? So I'm going to do some more acid-base chemistry here for you. So you're adding a strong base to a carboxylic acid. Okay, what happens when you add a strong base to a carboxylic acid? Could anybody who's on here right now tell me a strong base? Give me an example of a strong base. First one that pops into your head. Give me one example of a strong base that you would have learned in Introduction to Chemistry 1. In that class, you would have done an entire chapter. So potassium permanganate is not a strong base, no. Sodium hydroxide is a strong base, right? Any group 1 or group 2, group 1A or group 2A hydroxide is going to be a strong base. There's a couple of exceptions, but most of them, if you think of lithium hydroxide, sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide, right? Those are all strong bases. So a strong base, again, I'll write down the most commonly used ones would be something like sodium hydroxide or lithium hydroxide or potassium hydroxide, calcium hydroxide too. is a strong base. And again, that's something that you would have learned in Chemistry 101. So let's start. So since Larissa said sodium hydroxide, let's use that. If we take our carboxylic acid, okay, what would happen if you were to take just any carboxylic acid? Let's say you had acetic acid, okay? Let's use acetic acid. Okay, it's found in vinegar, it's cheap, okay? And if we take acetic acid, we have to fix that earlier. We take acetic acid, which again comes from vinegar, and we put it in sodium hydroxide. What the heck happens? Okay, what happens? Well, what happens is this, and I'm going to draw it in a little more detail here for you to kind of help you understand what the heck is going on. Okay, we have our sodium hydroxide, we have the sodium cation, and we have the hydroxide anion, like this. What happens is you have your acid, your carboxylic acid, and you have your base. Now, as you saw a few minutes ago, I said that a base is a proton acceptor. You could also call it maybe a proton taker, right? It just wants to take a proton. So here's my hydroxide, which is really the basic part. That is actually going to take the proton from the carboxylic acid, okay? It pulls it off of there, okay? And then the two electrons that are in this bond right here, they end up going on the oxygen. And when that happens, let's draw what you'd end up with, okay? You'd end up with this. You'd end up with the carboxylate. If hydroxide takes a proton, you end up with water. And then you also have the sodium cation. Now, the sodium cation is going to be close to the anion, right, because opposites attract, okay? So that's what happens. Now, notice that the arrow is irreversible. Since this base is so strong, it's going to take every proton it can from every carboxylic acid that's in the reaction mixture. So you end up with, this is called a carboxylic acid salt or a carboxylate salt. Both are acceptable. So a carboxylic, we call it a carboxylic acid salt or a carboxylate salt. Again, either one is okay. And if you're wondering, Mr. Dion, why is it called a salt? It's not table salt. Well, a salt in chemistry is any compound that's made from a metal and a non-metal, right? We can call those salts. So since sodium is a metal and oxygen, hydrogen, and carbon are all non-metals, this is called a salt. And then, of course, we have water, okay? There we go. And something that you would have learned in Introduction to Chemistry 1 was that an acid plus a base gives you a salt plus water, okay? You can always rely on your old general chemistry skills to help you in this class. Okay, chemistry is an additive subject. Well, let's see, it's 6:06. We got a little bit of time. Let's take a look at some more reactions here. I wanted to take a look at question 14. This is 14.51. And all it says here is complete each of the following reactions by supplying the missing portion of the indicated work. I kind of like these. They're kind of like organic chemistry's version of fill in the blanks, right? So I'm going to show you what it's got going on here. And I'm going to use bond line structure. So we start with acetic acid, or sorry, we start with acetaldehyde, and we want to oxidize that. Okay, we want to oxidize that, and it says, what do you end up getting? So I want you to take some time and write down what the product is, and then I'm going to take a look at this one. So let's see here, we have this 4 plus. And then over here. All right. There we go. Okay. I'll give you a couple seconds to think about these. And the only way you'd be able to solve these ones is if you read the book and watched the lecture videos that I had posted. All right, let's take a look at the first one. Now, can anybody give me an idea of what the product would be here in this first one, 14.51A? Could you name it? Well, we're starting with acetaldehyde or ethanal, whatever you want to call it. But I'll just use the common name. So this is acetaldehyde. And if we're oxidizing that, what happens when we oxidize an aldehyde? It gets oxidized to a carboxylic acid. So we're going to end up with a carboxylic acid. And the carboxylic acid is going to have 2 carbons. And so you end up with acetic acid. Acetic acid. All right, if we take a look at the next one, this is one of the most important reactions that is covered in this class. I didn't mention it tonight until now, but when we take a carboxylic acid plus an alcohol, we treat it with acid and we heat it up, we get what's called an esterification reaction, which is where we form an ester. We form an ester plus we get water. So where does the water come from? The water comes from here, H, O, and H. That's going to be our H2O. And then all we have to do is we draw the skeleton of what's left over here. So we have 1, 2, 3, 4 carbons. We have our oxygen, and then we have this methyl group here attached like that. So there's our ester and water. Again, that's an esterification reaction, one of the most important reactions you will learn in this class. The next one, we have cyclopentane carboxylic acid, keeps coming up tonight. We treat it with something, we heat it up with acid, and we end up with an ester. Well, this portion of the ester right here comes from an alcohol. And as you see here, we had a methyl group right there, and it came from methanol. And so the same thing will be required here. We're going to need methanol like this, okay? So again, these reactions here, and I'm also missing water, which should be here, but these 2 reactions, okay, these are esterification reactions, esterification reactions. All right, so the esterification reaction, if we just go over it quickly, and this will be the last thing we'll look at because we're going to have to leave soon for the lab, some of us. If we look at the summary of reactions at the end of chapter 14, the first one deals with the oxidation of a carboxylic acid, but the next one deals with esterification. Esterification, a very, very important reaction in organic chemistry. And the way esterification works is this. You start out with a carboxylic acid. So carboxylic acid. You combine the carboxylic acid with an alcohol. So I'll call R prime. We'll say it's a different R group. We have our alcohol. Then you treat those 2 together in some kind of glassware. You heat them up in the presence of acid, right? That's what H plus means. It just means acid. We have it in acid, and then you heat it up, okay? Then what do you get? From the carboxyl group, this portion here, and from the R group from the alcohol, you end up with an ester, okay? You end up with this ester, where this R prime group ends up in the place of the hydrogen. And then from this hydrogen and this hydroxyl, we end up with H2O, okay? However you want to write it. I'm the teacher, so I'll try to write it as neatly as possible, okay? So carboxylic acid plus an alcohol, you heat it up in the presence of acid, and you end up with an ester, and you also form water, all right? So what we'll do on what's today, Monday, on Wednesday night, is I would like to look at the hydrolysis of an ester. Okay, and I'd like you to look at that too, okay, and make sure you watch all the videos that I have posted. I spent a lot of time on them. There's 2 ways that you can hydrolyze an ester, okay? An ester can be hydrolyzed, and if you're like, what does hydrolyzed mean? It means broken apart. You can hydrolyze an ester in acid, and you can hydrolyze an ester in base. Okay? And when you hydrolyze an ester in base, it's got a really sassy name. It's called saponification. And I want you to be sure to watch all the rest of the videos for chapter 14, and I want you to be sure to try to do as many of the practice problems as possible. The best way to master the material in organic chemistry is simply to practice. If you don't get a pencil and a piece of paper in organic chemistry, it can be a very daunting subject without actually trying to draw the molecules yourself and putting in some quality time by doing that. All right, well, again, if you're in Group A, and that's the first half of you, you know who you are by now because we've met a couple of times. Again, tonight we're going to take a quick peek at the Alkanes Lab, which is a completely dry lab, no chemicals in that lab. You can do the whole thing at home, but I just want to go over a couple of little nuances about that with you. And then the lab that we're going to do that's going to require our safety glasses and our gloves and everything is lab number 3, which deals with hydrocarbon reactions. Please be sure to bring the pre-lab for both of those, and also bring your completed lab 1 with the pre-lab stapled on top, the pre-lab that I graded and gave back to you 2 weeks ago. If you don't have a stapler, do not worry. We have one at the community college, and you're free to use that. Okay, it's our free gift to you. Anyhow, all right.